Hello friends, hope you are doing well in your day-to-day life and profession, and we are moving ahead in our Six Sigma journey. So I welcome you to lecture 54, that is on acceptance sampling key concepts. This week we will discuss the various issues specific to acceptance sampling, and we are beginning with some key concepts on acceptance sampling. So I will keep reminding you that control chart are the most important tool, statistical basis, fact-based management to have control over my processes and take the appropriate action at the right time. So last lecture, if you recall, we had seen the detailed application of Minitab for variable control chart as well as attribute control chart, and now in this lecture we will try to appreciate the various concepts specific to acceptance sampling. So just see need of acceptance sampling, advantages, disadvantages, producers risk and consumers risk. Some new terminology you will be familiarizing, operating characteristic curve for acceptance sampling, types of sampling plan and evaluating sampling plans. So now just try to appreciate this figure and what does it tell. So let us say I have a supplier and 100% inspection is taking place at supplier's end, and then again I am taking the 100% inspection of the incoming material and then it goes to customer. So this is the situation 1. Now let us say supplier has produced situation 2, 100% inspection is taking place. Now supplier is giving the certificate that 100% inspection is taking place. I am just doing the sampling inspection and then it goes to my customers. Sampling inspection means I am not doing 100% inspection. I will just take sample. You all know what does it mean. Sample, a word we have used extensively in control chart. So even if you go to purchase wheat or rice, do you check the entire lot? Not possible. You will just take a small sample and try to check it. So same applies over here, that my supplier has done the 100% inspection. I may go with sampling inspection, accept or reject it, and then it will go to customer. Now just see that third situation in which my supplier has already established an external process control through control charts, statistical process control, and then I am just taking the sample and then passing the units to my customer. So you will see that the amount of effort is going down because I am trying to exercise better control over the process. But you will also see that when I am going for sampling inspection at this stage, second stage, then I need to devise my sampling plan in such a way that it really has a good discriminatory power. It means it should be able to say discriminate, separate out good lot from the bad lot and give me the right information. So if I can design such kind of system, a sampling plan, then I can avoid doing the 100% inspection. Similar way, if my supplier establishes SPC, then also with the better control, I can reduce my inspection effort and I can feel equally confident in accepting or rejecting the incoming or outgoing quality. So this is where we try to appreciate the importance of acceptance sampling. Just try to see a little bit a simple definition. What is acceptance sampling? So I would just like to emphasize that a procedure for sentencing incoming batches or lots of items without doing 100% inspection. So typically somebody is sentenced or sentencing, the word we use in the judiciary system, somebody is punished or somebody is exempted. But here what I say, that without doing 100% inspection, I will either reject the lot based on my sampling plan or I will accept it, and this decision I take based on my acceptance sampling. So this is what exactly we want to discuss as a part of this lecture. Now we can appreciate that why not 100% inspection? The reasons are very obvious. It is extremely expensive. Suppose non-destructive testing is required, you cannot do it 100%, otherwise you will spoil all the products. Then handling by inspector can itself induce some defects. Many a times when you are handling very precise parts and every part you are trying to inspect, then inspector can induce some defect that is not acceptable, and inspection typically becomes a tedious task, and in that case your inspector may make an error and defective items may be say accepted. So these are couple of reasons that I would not like to go for 100% inspection. So obviously I have the advantages: lower cost, smaller staff, less risk of handling damages, less time, helps in preparing the quality planning. So disadvantages are obvious with the acceptance sampling, that when you are only taking the decision based on sample, you may make a mistake in accepting a lot which is not good but of bad quality, or you may reject a lot which is actually good but you will declare it as a bad. So this disadvantage and risk we have to accept, and you cannot realize the benefit of 100% inspection when you are going for the sampling. But if you design your sampling plan appropriately, then you can really have better control over such decisions, and you can reduce the probability of making say wrong decision in either case, whether accepting the bad lot or rejecting the good lot, and that can really give you more or less the same confidence that otherwise you can have through 100% inspection. So let us try to see the broader domain. So when I say statistical quality control, we have seen the statistical process control, variable chart and control charts for attributes, and now we are discussing the second pillar of this, that is acceptance sampling for variables and acceptance sampling for attributes. So the simple is very simple, that you have statistical quality control, process control, acceptance sampling. Within process control you have the control charts for variables, control charts for attributes. Similar way, attribute sampling, you have the attribute sampling plan for variables as well as attributes. So this is how we try to appreciate the concept of statistical quality control, and there could be couple of typical points where you would like to employ the acceptance sampling plan or the inspection level as desired. So it may be raw materials and purchase parts, it is coming to your processes. So if there is some bad quality, that will have a significant impact on the quality of your produce, final product, and your processes will also not be able to accept such variation. Finished products before a costly operation, because your entire value will be lost if your input material is not good, then before an irreversible process. All these are the examples where you have very high risk of losing the value, and it is always better to employ inspection or an adequate sampling plan, so that I actually process the good quality component or work in process inventory or the raw material, so that my operations cost value addition is not wasted. So this is where we can realize the importance of acceptance sampling. So what is an acceptance sampling? In a very simple way, set of procedure for inspecting incoming material or finished goods based on some rules, not the 100% inspection. So typically couple of points that I consider when I talk about the design of the acceptance sampling plan. This includes my type of sample, sample size, criteria used to reject or accept the lot, and most importantly, producer and consumer must negotiate, because when you go for sampling, they both have to accept some amount of risk, that is the stipulated risk, and this risk is called consumer's risk and producer's risk, and they must agree, negotiate on this, so that even if there is a probability of making some mistake, wrong decision, it should be acceptable to both the party. So these are some of the things that we try to incorporate in the design of acceptance sampling plan. So I will just refer the notations like this. Capital N, when I say, it is the lot size, small n is the sample size, C is the acceptance number, and D is the number of defective items in sample. So the rule is very simple. D is less than or equal to C, so number of defectives is less than or equal to C. You accept the lot. If it is greater than, reject the lot. So I have predefined acceptance number, rejection number, and if let us say number of defective D is less than or equal to acceptance number, then I will accept, otherwise I will reject. So this is how I try to develop and design the sampling plan, but we need to go deeper in order to appreciate the inclusion of producer's risk and consumer's risk and design a sampling plan which has a good discriminatory power, meaning to say separating the bad lot from the good lot and satisfy the requirement risk acceptance of the producers as well as consumer. So just try to see, it would just be a revision. Type 1 error we have already discussed, punishing an innocent person when he is actually an innocent, not guilty, it is type 1 error, and not punishing a guilty is type 2 error. So same concept I will use here. Instead of a person, here it is a lot. So I will say type 1 error or alpha error or producer's risk. So this occurs when my sample says that parts are bad or the process is out of control, when the opposite is true. I am rejecting the good quality lot based on sampling, and this is called type 1 error. My producer is at risk. My producer has shipped good quality component, but based on a sampling plan I am rejecting it. So this is my type 1 error. If you see the type 2 error, beta error or consumer risk, whatever you say, it is the same thing. In this case, typically I am accepting the bad quality product and say that the bad quality product is of acceptable kind, and this is where I as a consumer is at risk. So we must appreciate producers and consumer risk very well, so that this can be appropriately incorporated in design of sampling plan. So just try to see this figure, and that will give you the fantastic clear cut idea on producer's risk and consumer's risk. Just see this. This is the decision and this is the truth. So your decision and truth must align. When they don't align, you make a mistake. So let us say I have a good lot and I say my decision is reject. This means it is a producer's risk. Producer has put all the effort, value addition, gave me the good lot, I am saying it is reject. So this is my type 1 error. Now I have a bad lot and I accept. So I as a consumer is at risk, and this is called consumer's risk or type 2 error. And if you see this diagonal, then my decision and the truth, they are matching. When I say bad lot, I reject, so no error. When I say good lot and I accept, it is no error zone. So these are the 2 points which are of my concern, and that really creates the problem. So I have to have the say typical trade-off between my producer's risk and consumer's risk in order to devise a good discriminatory sampling plan. So just see, type 1 error is probability of reject good lot, and typically this is called producer's risk, alpha, same notations, and if nothing is given, I will accept 5% as a common producer's risk. Similar way, type 2 error, probability of accepting bad lot. So this is called beta or consumer risk, and 10% is a typical value when nothing is given. So 5% as producer risk is the standard value, 10% beta consumer risk is the standard value when nothing is given, and I would like to develop my acceptance sampling plan with this alpha and beta. So now let us move ahead. That again, when I have to talk about the discriminatory power, I have to talk about the goodness of my control system. I must talk about the operating characteristic curve, and exactly the way we have developed the operating characteristic curve for the control charts, I also need to use this concept of operating characteristic curve in order to check the performance of my, say, acceptance sampling plan. So curve that illustrates graphically the probability of accepting the lot that contain different % defective discriminatory power is basically the operating characteristic curve for acceptance sampling. Now just see this, and it would really be interesting to appreciate. Now let us say I have say cutoff point 4. It means anything which is less than 4, I will keep the whole shipment, and 4 is what? Percentage defective in a lot. Suppose let us say you have a lot of 100 items. Out of this 4 items are defective or 3 items are defective. If it falls below 4, I will accept the entire lot. Suppose if it exceeds this cutoff as a threshold point, I will return the whole shipment, and my decision is based on sample. I am not doing 100% inspection. Now, do you see the fallacy with this concept? Do you see any fallacy with this concept? So this is called perfect OC curve, because there is one line. When exactly you reach to this line, it tells you that either you accept or you reject. But do you think that when you move from 0% defective to 1% to 2% to 3%, your probability of acceptance will remain same? I don't think so. As the percentage defective increases, you must have change in your probability of acceptance, which is a quite, say, wise and realistically designed operating characteristic curve, rather than I go for the perfect OC curve based on 100% inspection. So now when I cannot operate with this and I have to go for the sampling, just see this, and this would really help you to appreciate. I have a cutoff and I am going for less than 100% inspection, and I have a cutoff, let us say 3. Now what do you see here? I have the OC curve, and 100% means when there is 0 defective in my lot, when I am doing based on sampling, I will accept 100% acceptance. When there is 1%, the probability changes and I will be maybe close to 95%. When it is 2, my probability will further reduce, it would be maybe 93% or 90%. Same way I will have reduced probability. So here what you can appreciate, that I have reducing probability as the number of defective increases in the lot, and this is where I can really feel happy and realistic about my operating characteristic curve for acceptance sampling plan. So this is for less than 100% sampling. The previous one was for 100% inspection. Now just see this in order to make it more elaborative. Here my cutoff is, let us say, somewhere 4, and now I am writing something here type 1 error, I am writing something here type 2 error. What does it mean? It means that actual percentage defective in lot is, let us say, 4%, and then I have a particular region. So here if I reject the lot, my producer is at risk. So this is called my producer's risk, because percentage defective is less, then also I reject the lot, then my producer is at risk. When I go for higher percent defective, and suppose if I accept the lot, then I as a consumer is at risk, and this is typically called type 2 error, and it is my consumer's risk. So when I refer with respect to cutoff, then both the party they have to accept some risk. When any lot which is rejected, which is less than cutoff this side, then my producer is at risk. So producer's risk, any lot which is accepted by the consumer which has more percent defective than the cutoff, it is my consumer's risk. So this is exactly where I have to see the trade-off. And now let us see how would you like to construct the OC curve for particular acceptance sampling plan. So let us take some data, construct an OC curve for a single sampling plan where the lot size is 2000, this is the complete lot, and from that lot you are taking the sample of 20. So there could be many samples you may take, but the lot is of 2000 and the acceptance number is 2. So now let us see how can I construct the OC curve for this. So the given data is like this: n is equal to 2000, n is equal to 50 and c is equal to 2. So what I say that let us say my p is 0.02, that batch is 2% defective. So the probability of lot acceptance is equal to the probability of obtaining 2 or fewer non-conforming items, and I am assuming my p as 2%, that is 0.02. Now if I just compute NP, so your n is let us say 50, that is the sample size, and p is 0.02. When I multiply this I get 1. Now NP is 1. So once again we discussed previously, I will refer the cumulative Poisson distribution table, which basically relates the value of mean with respect to the value of x or particular number. Here my number would be c. So let us see that for the given acceptance number c, my probability will be 0.920, and this probability is called PA, probability of acceptance. So now I can just try to calculate the probability in the same way, and what do you see here, that let us say I am taking the different values of P, initially 0, then 0.005, then 0.01, 0.02, it means 2%, 3%, 4%, 5%. Same way my NP will change, and for the given NP I can find out my probability of acceptance from the probability Poisson probability table. So once I found this PA, which is the probability of acceptance, and I have the value of P, then my task would be simple and I will plot the OC curve. So you can see here that on x-axis you have the proportion non-conforming, so 2%, 4%, 6%, 8% and so on, and you have the probability of acceptance which you have determined from the cumulative Poisson probability table, and this particular acceptance sampling plan is for n is equal to 2000, that is the lot size, small n is equal to 50, that is your sample size, and c is equal to 2, that is the acceptance number. So now what do you see here? You see a curve, and this curve has a discriminatory power. So what exactly you say, that when you have 0.04, when you have 0.04 means 4% defective in your lot, proportion non-conforming or proportion defective, then what is the probability of acceptance? So you can very well see that when I have less percentage of defective or the non-conforming proportion, my probability of acceptance is high. My probability of acceptance is high, gradually my probability of acceptance is reducing, which is obviously a desired feature of my operating characteristic curve. But obviously you cannot have same shape. You may think about a shape like this, you may think about a shape like this, you may think about a shape like this, and if you go more steeper, then your discriminatory power increases. So it all depends that what is your quality characteristic and what could be the consequences of accepting a bad quality part or rejecting a good quality lot. Depending upon that, you need the discriminatory power of your acceptance sampling plan. So once you have appreciated this, then you can also see the effect of sample size and acceptance number. I can change my sample size, I can change my acceptance number, and I can just try to see that what is its impact on the discriminatory power, it means slope of my OC curve. So just see this and the idea will be extremely clear. So you have a sampling plan where n is equal to 2000, small n is 50, c is equal to 2. So I have a lot of 2000, I have a sample size 50, I have acceptance number 2. You just see what I am doing, I am just keeping these values same, I am just keeping these values same. So capital N and C I am keeping constant, I am just changing the value of sample size, and you will see that for 50 sample size it is this one, for 100 it is this one, and for 200 it is this one. It means if I just draw a line here, then for same percentage proportion non-conforming, if my OC curve is highly discriminatory, which is this one, having let us say higher sample size, then probability of acceptance is very low. Probability of acceptance is little higher and probability of acceptance is very high. So it all depends what is your quality characteristic, the kind of product you are dealing with. Suppose you are making a very precise component, purchasing it from a supplier. Typically I visited HAL, Hindustan Aeronautics Limited, and they have many indigenous suppliers as well as they have many foreign suppliers for the purchase of highly precise components for aircrafts. Now you can see that the aircraft safety is something which is of highest order and you cannot compromise with the quality. But if you think about some nuts and bolts used in some ordinary manufacturing company, then you may not need that much of discriminatory power of the OC curve. But if you talk about aircraft, then you may like to go for little higher discriminatory power of the OC curve. So I just want to show you that there is an impact of the sample size on the say discriminatory power of the OC curve. Obviously my cost of inspection will increase. So this is something that you can appreciate. Now just see what I am doing. Effect of the acceptance number on the shape of the OC curve. I am just changing the acceptance number 3. This is the one. I am tightening it to greater discriminatory power, 1 greater discriminatory power, 0 greater discriminatory power. These values are kept constant so that I can see the impact of C on change in C. So as I am reducing the acceptance number, I am developing more and more tighter say acceptance sampling plan. The discriminatory power increases. Obviously this will have an impact on my producer's risk as well as consumer's risk. So this is something that we can appreciate. Now if you see the types of lot by lot sampling plan and what is the variety, then you have single sampling plan, double sampling plan and multiple sampling plan. Single sampling plan, I will take the decision based on a single sample, and information obtained from one sample is used to make the decision about accept and reject, and typically your sampling plan will have sample size n and the acceptance number C. If I go to double sampling plan, I will take the decision in the first go if my number of defective parts are less than the acceptance number. fine, it's a good quality lot, I will accept it. But if not, I will not stop there. I will take the another sample and then I will take the cumulative number of defective, both sample 1 and sample 2, to compare it with the, say, acceptance number for the second sample, and then I will take the decision. Multiple sampling plan, you can extend your double sampling plan, keep taking. So basically you will have C1 and small n1, you can have C2 and small n2, or if you keep n same, then you will have C1, C2, C3, C4, and you can just extend your double sampling plan to see that what decision you can take appropriately about the acceptance or the rejections of the lot. So I am just giving you the introductory idea. In detail we will see the design of single and double sampling plan in the subsequent lectures. So now there are obviously some advantages and disadvantages with the plans. Single sampling plan are very simple, and maybe the record keeping, training and other thing is very less, which is quite high in double sampling and multiple sampling. But on an average, for equivalent plan means the discriminatory power, the number of items inspected to make a decision regarding the lot is usually more for a single sampling plan. This is because double and multi-level sampling plan use fewer items in their sample if the lots are very good or poor. So obviously single sampling plan, my inspection cost will be little bit higher when I take only single sample which is of a larger size. Evaluating sampling plans, this is an important thing. So we will try to see couple of performance measures. Number one, which is very important, is average outgoing quality. So please try to appreciate this properly. Average outgoing quality is defined as the average outgoing quality is the average quality level of a series of batches. I am taking series of batches, please emphasize on this, series of batches that leaves the inspection station assuming rectifying inspection. It means suppose a particular batch is rejected, then rectification means I will replace the bad quality product with the new one, and then only I will allow it to go to the next stage. So after coming in for inspection at certain quality level, that is percentage defective, proportion defective. So AOQ is defined as, please refer it carefully, PA, probability of acceptance, P is your incoming lot quality, proportion non-conforming, capital N is my lot size, small n is sample divided by n. So this is a very important definition, average outgoing quality. It incorporates, to remind you, the concept of rectification. So AOQ measures the average quality level of a large number of such batches, not one batch, large number of series of batches or sub batches of incoming quality with P, proportion non-conforming in the lots assuming rectification. So now if we just do a little bit computation, then I have, let us say, incoming lot quality 0.01, 0.02, 1%, 2% and so on, and I can compute PA, probability of acceptance, and I have average outgoing quality. So you just plug in the values of P, PA, you have the capital N, small n, and typically PA you can find from Poisson, cumulative Poisson table, already we have discussed, and you will have the average outgoing quality. So you have basically N 2000, N 50 and C is equal to 2. So with this data set, you can plot the average outgoing quality curve, and what you see here is something maximum. So average outgoing quality limit or average outgoing quality level, it is the highest level that will be passed to the next stage. Now what I can infer from this is my incoming lot quality, so 0.0, 0.02, 2%, 4%. So my proportion non-conforming is increasing. This is my average outgoing quality. What is happening? average outgoing quality is increasing up to a particular point and then it goes down. So, incoming lot quality, as it worsens, my average outgoing quality is going down. Initially it increases. Now, why this happens? So, it is interesting to see that when the incoming quality is very good, fantastic, means your proportion non-conforming is less, the average outgoing quality is also very good, that is obvious. Now, consider the concept of rectification, and what happens that when the incoming quality is poor, the average outgoing quality is good because most of the lots are rejected and through a sampling plan go through screening in between, and you will have something like AOQL between these two extremes, which is the maximum limit of AOQ, average outgoing quality. So, typically I can define this maximum limit AOQL is average outgoing quality limit is the maximum value or peak of the AOQ curve, and typically it represents the worst average quality. Please remember, it is the worst average quality that would leave the inspection station. Then after, when the lots have started rejecting, I am applying the same rectification and replacing the bad quality products with the good one. So, my curve is going down, but AOQL is the peak, which is the worst average quality that would leave the inspection, assuming rectification regardless of the incoming quality of the lot. So, this is something that we can appreciate, that protection offered by the sampling plan in terms of AOQL value does not apply to individual lot, it holds the average quality of a series of batches. So, this part we must appreciate. Now, there is another performance measures for my operating characteristic curve or acceptance sampling plan typically, and this is called average total inspection. So, average number of items to be inspected per lot, and you can put it like this, that suppose I have sample size n, then n is inspected plus 1 plus PA n minus n. So, n is your total lot minus n, which is already inspected, and 1 plus PA is the probability of acceptance. So, I can expand it for the double sampling also, and I can have n1 PA1, n1 plus n2 PA2, and then capital N 1 minus PA1 minus PA2, it is a double sampling plan. So, when you analyze this data, let us say you have n is equal to 2000, n is equal to 50 and c is equal to 2, I can just plug in the values in my equation. So, 50 plus 1 minus 0.920, PA is 0.920, 200 minus 50. So, I can plug in these values here, and what I can found that I can compute the series of values of ATI for the incoming quality and probability of acceptance. So, when you do this, you will have a typical curve which is called average total inspection, and what you can see here that my average total inspection increases for a given n is equal to 2000, n is equal to 50 and c is equal to 2 as my incoming lot quality is becoming bad. So, fine, it is obvious, but again you can choose the appropriate level of inspection depending upon the criticality of the quality characteristic and the consequences. So, this is what we can talk about ATI. There is another measure which is called ASN. So, ASN is basically average sample number. This refers to average number of items inspected for a series of lots with a given incoming lot quality to order to make a decision is known as the average sample number. You need to take the decision whether it is of good quality or bad quality. So, it is the average number of items inspected for a series of lots with a given incoming lot quality in order to make the decision. So, suppose I have 3 non-conforming items are found by the 20th unit. When using a single sampling plan, when you have n is equal to 800, n is equal to 60 and c is equal to 2, what will you do? N is equal to 3, so you will say that you can take the decision on 28th because it is exceeding your c is equal to 2, but you will not stop here. You will continue after the 28th unit to reject, you will continue your inspection up to 60. So, I want to understand that under this assumption, the average sample number for a single sampling plan is equal to the sample size n. So, ASN, in case of double sampling, you can just expand it and you will get the value of ASN. So, now if we just try to do little bit analysis, then it is not that difficult. Suppose let us say the number of items inspected before making a decision is n1 or n1 plus n2. Now, P1 is the probability that a decision will be made after n1 items are inspected, and the probability of inspecting n1 plus n2 is, say, items prior to making decision is 1 minus p. Now, if I find the probability P1, that is equal to probability of lot accepted on first sample plus probability lot rejected on the first sample. So, both I can consider. C is the acceptance number, R is the rejection, X is less than or equal to C1, that is the probability specific to lot accepted on first sample, X is greater than or equal to R1, lot rejected on the first sample. When I do this, X represents the number of non-conforming items, C1 is the acceptance number and R1 is the rejection number. You can also do it for the multiple sampling. So, basically my purpose here is to find the ASN, average sample number, and if I just do the analysis for this particular sampling plan where n is equal to 300, I am talking about the double sampling, C1 is equal to 1, R1 is equal to 4, N2 is equal to 80, C2 is equal to 3 and R2 is equal to 4. So, you can see that you have C1, R1, N1, C2, R2 and N2. This is my double sampling plan, and proportion non-conforming is 0.02. Assuming no curtailment, I will continue. Even if I can detect that my lot or my particular sample is of reject level. So, I will apply this P1 is equal to probability x1 less than or equal to C1 plus probability x greater than or equal to R1. I can plug in the values for N1P this and N1P this, and you can again refer the Q1 cumulative Poisson table where you can refer the mean as well as the number of x, and you will get the values of probability. So, you can put these values and you will find that ASN is 54.56. So, with this understanding, I can just extend my calculation for multiple points, and what you can do here, that you have incoming lot quality P 2%, 3%, 4%, 5%, you have probability of acceptance that you can find, and you have average sample number. So, once you have the average sample number, you can plot this on a graph and you would get something like this. So, what does it mean? That n is equal to 3000, n1 is equal to 40, second 80, 1, 3, 4, 4. So, I have the average sample number to be inspected in this fashion. So, initially when my proportion of non-conforming increases up to this point, average sample number is increasing, then my average sample number to be inspected is gradually going down with proportion of non-conforming, maybe more number of lots are rejected, and that could be the reason that my average sample number is going down. So, before I end, let me float couple of think it, discuss the advantages and disadvantages of the sampling, distinguish between producer's risk and consumer's risk and try to explain it with some suitable example. What is the importance of OC curve, and describe the impact of sample size and acceptance number on the OC curve. So, try to answer this question, that will help you to have a good internalization of the concept and better clarity on the concepts covered. So these are the references I have used for this particular lecture material. You can also refer it. So acceptance sampling is a branch of your statistical quality control and extremely useful in deciding the discriminatory power of my acceptance sampling. When I don't want to go with 100%, I want to go with a sampling procedure. Acceptance sampling gives me a confidence by designing an appropriate sampling plan in my decision of accepting or rejecting the lot. So thank you very much for your interest in learning the concept on acceptance sampling, the basics we have discussed. Keep revising, try to introspect, solve with some hypothetical data as I recommend, and practice the concepts covered in various sessions for your better introspection. So be with me, enjoy.